Alright, so today we're going to be talking about hypothesis testing. So, we have our esteemed colleague here today, Sakeem Freeman. Do you know what a hypothesis test is, Sakeem?
No, I do not.
Well, I'm here to explain that concept to you. A hypothesis test is when you have a particular sample and you're trying to see if that sample is rare enough that you can reject and apply certain conditions to the entire population parameter. So, Sakeem, I was really curious, do you know what a null hypothesis is?
I do not know what a null hypothesis is.
Okay, so a null hypothesis is the first part of the hypothesis test. This is stating what's already accepted as true. This is what the population already accepts. Sometimes it's written as the p is equal to 0, the mu is equal to 0. It's what we already can expect. Now, what is the alternative hypothesis? Do you have any idea?
What you are trying to prove.
It's almost like you read it from my memory. Here's the deal. The alternative hypothesis is what you are trying to prove, almost word for word, what you exactly just stated. So here's the deal. What we're going to be doing with an alternative hypothesis is generally you're going to find one of these three options: less than, greater than, or does not equal to. We will always say that the null hypothesis will be equal to something. Now, less than means you're using a p-value to the left of the standard normal curve. If you're using greater than, you're going to find it to the right of the normal curve. Now, if it does not equal to, what you're going to be doing is adding the p-values of both sides, because you're saying you're not quite sure where the other fact is. In terms of this is equal to, we just know that this is not true. Alright, so before you can actually conduct a hypothesis test, Sakeem, there are certain conditions you must meet. Did you know that?
No, what?
Alright, so there are three main conditions that you have to meet for any hypothesis test: SRS, independence, and normality. What do you think an SRS stands for?
Sakeem's really supreme.
Close enough! It's a simple random sample. This means that the sample that we're using to estimate the parameter is taken randomly. It's not a specific group. Therefore, it eliminates bias and could give skewed results. As long as we have a simple random sample, we avoid all that. Now, the next condition is independence. What do you think independence is, Sakeem?
I don't know.
Yeah, that's about it. So here's what independence is. Independence is stating that the sample is small enough that the entire population isn't being affected by it. So generally the rule for independence is that the sample has to be less than 10% of the population. If it's greater than that, you could get skewed results. So the way we calculate this, if we assume that the population is p, that p has to be greater than 10 times n, where n is the sample space. Now, our final condition that we work with is normality. What do you think normality is, Sakeem?
Me.
Yep, that's true. Normality, in this case from a mathematical perspective, is when you're trying to see if the graph is symmetrical and would fit a standard normal curve. Now, for a t-test, you're going to have the same thing as a z-test. Now, in this case, what that means is that if the sample size is over 30, we can use the central limit theorem stating that all sample sizes over 30 are approximately normal to say that this condition is met. Now, if we're working with proportion, what you're going to find is that you have to do two calculations. The number times the probability has to be greater than 10. And then you also have to do the number times 1 minus the probability is greater than 10. This calculates to make sure that the approximate proportions, if you could graph it, are about the same and therefore normal. Alright, so the final step when you're conducting a hypothesis test is the conclusion. Now you have two options in the conclusion, Sakeem. What do you think those two options are?
Fail to reject and reject.
Brilliant, Sakeem! So here's what you're going to do. If you fail to reject, that means your p-value is greater than the significance level, or alpha, that you have accepted for the problem. If you reject, that means the p-value is smaller than the overall A value, alpha, and therefore we can make some conclusions stating that the alternative hypothesis will be accepted instead. Isn't that interesting?
It really is, it really is.
All right, Psyche, here's what we got going on here today. We have 3 types of hypothesis tests. Did you know there are 3 types?
Nope.
All right, so here are the 3 types. You have a one-prop z-test. A proportion test is when you're given a proportion of the population and you're given a proportion of a sample, and you have to figure out if the proportions match or if the alternative hypothesis is true given the alternative hypothesis. Now, a t-test is used when you don't have the population standard deviation. What you use instead is degrees of freedom. Now finally, a z-test, which is the most basic type of test, is when you are given the population standard deviation, and therefore you are able to calculate using a normal curve instead of a t-curve to find out if the proportion and the p-value is less than the significance level. So let's go over some specific vocabulary with hypothesis testing. So this, what does that look like to you, Psyche? An A? Close enough. This is alpha, and alpha is the significance level. Generally, the alpha is at 0.05. Sometimes it can be 0.1, sometimes it can be 0.01, sometimes even 0.001. That is where you are going to be evaluating the p-value. If it's less than the significance level, then you're going to reject the null hypothesis. If it is greater than the significance level, then you're going to fail to reject it. Now, the p-value is another thing that I've been talking about. What do you think a p-value is?
P. Diddy.
P. Diddy. Close enough. Here's what a p-value is. The p-value is the probability of a certain sample occurring when the given parameter is true. So we use this and we calculate this using our calculators. Very interesting stuff. So what we're going to find is that if our p-value and the significance level are related, in that if this is really, really small, smaller than this, we're going to reject it. If this is bigger, well, you know, we're still going to reject it. But if this is bigger than the significance level, then we are going to fail to reject the null hypothesis.
What's good, brother?
What's going on, Connor?
So basically, type 1 error is basically when the null is rejected when it shouldn't be. Type 2 error, well, as you can see, it's basically when the null is felt to be rejected when it just shouldn't be. And so yeah, that's basically what that is.
I'm so proud of you, Connor. Good job, Psyche.
Thanks, Ronald.
Thank you, Ronald.
All right, so the final part of type 1 and 2 error is power. Now, power is calculated by taking just a 1 minus the type 2 error. This indicates how often we correctly reject the null hypothesis. This is really, really good if you have a high number like 0.89, 0.95. The lower the power, the less accurate the tests are going to be, so you always want a high power. Now, one time that you're not necessarily going to be doing the same things is if you have 2 samples that you're using to measure against the population. What do you think that's going to do if we have 2 samples instead of 1? It's going to complicate our lives. So here's what we're going to do. Instead of the null just being mu is equal to 8, what we're going to find is that it's going to be the proportion of 1 sample is equal to the proportion of 2 sample, or the mean of 1 sample is equal to the mean of another sample. These will become the new null hypotheses. Another difference is that it will apply the same way for the alternative hypotheses. What you will find is that it does not equal P1 or P2, or does not equal M1 or M2 are examples of that. Now, if we move over here just for a second, the conditions for the most part stay the same. So what you're going to find is the SRS must remain true for both samples. Now, independence is also the same in terms of they both have to be independent. We can calculate this by using the same formula again. Now, for normality, things get a little different. The CLT still does apply. Now, instead of NP greater than 10, what you're going to find is NP greater than 5, because it's going down to the 2 sample. Now, you have to calculate that for both proportions. So what you're saying is if you have two different proportions, you have to do this calculation 4 times, twice for each proportion, so that you can meet the normality conditions. Now the conclusion is going to be pretty much the same in terms of fail to reject or reject that either this is true or this is not true. And that's what you're going to do if you have 2 sample tests of any sort.
Alright, we will now be performing a 1-sample proportion z-test. A survey claims that 9 out of 10 doctors recommended aspirin for their patients with headaches. To test this claim, a random sample of 100 doctors is obtained. Of these 100 doctors, 82 indicate that they recommend aspirin. Is this claim accurate? We'll use an alpha of 0.05. So our null hypothesis is that p equals 0.9, and our alternative hypothesis is that p does not equal 0.9. For our SRS, it is indicated in the question, so we're good over there. For our independence, our population for doctors is obviously greater than 10 times 100, so we're also good over there. And for our normality, we have to do n times p, n times 1 minus p. So once we do that, we get 82 and 12, which are both greater than 10. Then since we're good for the conditions, it is okay to use a 1 proportion z-test. And once we run a 1 proportion z-test in our calculators, we get z equals approximately negative 2.67, and with a probability of 0.008. And since our probability, which is equal to 0.008, is less than 0.05, we reject the null hypothesis and assume that the assumption 9 out of 10 doctors recommended aspirin for their patients is not accurate. Alright, we will now be doing a z-test. The ACT has longest stated to have a mean of 18 with a standard deviation of 6. We wonder whether that average is still accurate. Let's assume we collect a random sample of 50 high school students from all over the country and find their average is 20.1. Is this enough evidence at the significance level of 5% to conclude that the stated average score of 18 is incorrect? So our average the null hypothesis is that the average ACT score is 18, while the alternative is that it does not equal 18. So for our conditions, SRS is indicated in the question, as I read before. For the independence, the population is for students who take the ACT is obviously greater than 10 times 50. Then for our normality, we use the central limit theorem because this is a z-test. So 50 is obviously greater than 30, so we're good over there too. So in this case, it's okay to use a z-test. So once we do a z-test in our calculator, we can see that z equals 2.47 and our p-value equals 0.013. And since 0.013 is less than 0.05, we reject the null hypothesis and assume that the average ACT score is not equal to 18.
So this is our t-test question. A medical researcher wishes to investigate the effectiveness of a new weight loss fitness program, which is thought to increase the amount of weight loss. The original version is said to have caused people to lose an average of 8 pounds over a 2-week period. The new version is tested on a volunteer group of 35 students over a 2-week period, and those 35 students lose an average of 8.7 pounds with a standard deviation of 1.4. Are these results significant at the 10% level? So our null hypothesis is that the mean is equal to 8 pounds, and we are proposing that it is greater than 8 pounds. So we run through our SRS, and it is a volunteer, so we can't know if it is actually random, so we must assume independence. It is very easy for us to test more than 350 students, and for normality, 35 is greater than 30, so our CLT guarantees. So it is okay to use our t-test. When we run our t-test, we get our t-score of 2.9 and a p-value of 0.002, and since that 0.002 is less than 0.10, we reject the HO and assume that the average weight loss is more than 8 pounds. A researcher conducting a medical study to investigate whether taking a low-dose aspirin reduces the chance of developing colon cancer, and they had 1,000 adult volunteers who were randomly assigned to 2 groups, one of the placebo and one of the aspirin. At the end of 6 years, 15 of the people who took the low-dose aspirin had developed colon cancer, and 26 of the people who took the placebo developed colon cancer. At the significance level of alpha equals 0.05, does the data provide statistical evidence that the taking of the low-dose aspirin each day would reduce the chance of developing colon cancer? So our null hypothesis is P of the aspirin, a proportion of the aspirin minus the proportion of the placebo is equal to 0, and we're proposing that the proportion of the placebo is actually less or greater than the proportion of the aspirin. So as you can see, all the conditions were met for each of them. Independence was also easy done, and normal was done as well. So when we do conduct the two proportion z-test, we get a z value of 1.75 and a p-value of 0.04. And since 0.04 is less than 0.05, we reject the alternative hypothesis and assume that the proportion of the difference with cancer is smaller if they take the aspirin.